All right. Can you hear me? Can you hear me now? Yes? Okay. Thanks. Okay, sorry for the delay, and thanks, Alex, for introducing me. So I'm going to tell you my final lecture about these impurity models. And so the first part of the lecture will be devoted to calculating entanglement entropy in this model. And in the second half, as I promised, I will talk about this Such-Diffie-Taif model, which generated quite a lot of attention recently. And well, this is a whole subject on its own, but I will put it into the context of the things I've been discussing here. All right, let me start with the entanglement entropy. And so as you are probably, right, okay, let me write the headline. So entanglement entropy in the holographic Kondo model. So by the way, if you want to read about these things are everything I'm going to say is about pretty recent papers. So this is 1511-03-666. And okay, so let me remind you, so entanglement entropy I'm going to abbreviate with EE. So let me very quickly remind you about the holographic entanglement entropy as proposed by Ryo and Takayanagi, and then we'll apply this to our model. And so there's this very, very famous paper by Ryo and Takayanagi, which is heptate 060301. And so, well, they were doing the following. So let me first review the field theory definition. Of the entanglement entropy is as follows. So consider two space-like separated regions. So this is region A, and the complement of it is region B. And then, we define a so-called reduced density matrix which is associated to the region A, and this is obtained by tracing over the states in region B over the total density matrix. And essentially what this means, so this is the entropy for an observer in A who cannot access information about B. So this is a prototype thinking of A as somebody who's outside a black hole who cannot gain information about what is inside the black hole. So let me write this entropy for an observer in A who cannot access information about B. Okay, and now, so this is something which can be evaluated in field theory, but so the proposal of Ryo and Takayanagi was that in holography, you can actually calculate this quantity by the area of a minimal surface in the additional dimension. So now this plane with A and B, okay, I put this in and try to draw in 3 dimensions, because then now we add an extra dimension, which is our radial direction, C. And so then in this anti-de Sitter space, you calculate the area of this minimal surface, which whose boundary coincides with the boundary of A. And so then their proposal was that the entanglement entropy for this region A is the area of the surface gamma A, so this is the surface, divided by 4g Newton. So which is clearly inspired by the black hole entropy. So gamma A is the minimal area with the boundary of A coinciding with the boundary of gamma A. Okay, so obviously since ADS is a non-compact space, this is actually going to diverge and regularization is required. Okay, so this is a general result, but this can be applied to various examples, and the example for us, of course, will be the BTZ black hole, because that's what we're going to need to look at our impurity. And so in this very first paper on the entanglement entropy, Ryo and Takanagi applied their expression to the BTZ black hole. And by defining the usual inverse temperature to be beta, they found that SA calculated according to this formula is given by C thirds. So C is the central charge of the dual conformal field theory, and then there's a log of beta over pi times epsilon, where epsilon is a cut of the boundary, which we need for regularization. And then there's a hyperbolic sine of pi times L over beta, where now this L is the entangling region since essentially when you are in, so if we are in a BTZ black hole, this means our gravity space is three-dimensional, then the boundary space is two-dimensional, and then so the space-like surface will be just a strip of length L. Okay, so essentially then the surface, which you can't see because it's behind the board, this just becomes a geodesic essentially. Okay. So what you have to calculate now, if this is your ADS direction, you have to calculate the length of this geodesic over this length L, the boundary. The central charge in ADS CFT, you can calculate in terms of the conformal anomaly, or as the coefficient of the conformal anomaly, and so L is the anti de Sitter radius, and then you have L over 2g Newton, and if you put in all the quantities of the ADS CFT correspondence, this will just give you a number which is actually proportional to n. Okay, but the interesting thing is that this gravity result which they got actually coincides with a field theory result which was obtained by Calabrese and Cardi slightly beforehand. So this was Cardi. Which is, of course, a nice success. Okay. So let me write the reference. I have TH 0405 152. Okay. Now let's go to our impurity. Okay. As I mentioned at the end this morning, so clearly what we have to do is to calculate a length of a geodesic, and unless we include the back reaction of our defect on the ambient geometry, we won't see any effect of the defect acting on this geodesic. So what we have to do is to include the back reaction, and eventually what we want to do is, so again, we have this strip of length L, And then now we put this impurity here. Oh, okay, it's too small, you can't see it probably. So this is the impurity sits here. And then if this is our radial direction, okay, so here you want to calculate this geodesic, and you want to see how the length of this geodesic changes when you put this impurity here. And there's also a nice way of regularizing, okay, so because there's this epsilon here, because we can calculate the difference of the impurity, the entanglement entropy with and without the spin being present. And that will give us a finite result. And actually what I'm going to show is that what the gravity result which we obtain coincides with a known field theory result. So this is a nice confirmation of this approach. Okay, so clearly we have to include the back reaction of the ADS2 defect on the 3D geometry, because otherwise the geodesic will always have the same length. Okay, and so then what we're going to calculate is a quantity known as the impurity entropy, so which is going to be finite due to this regularization which takes place, and so this will be the entropy of a strip L at a temperature given by beta, and then we take the impurity, the entropy, or the entanglement entropy with the impurity minus the same entropy, so the entangling region is the same, the temperature is the same, but then we consider the case without the impurity. But that's simple because Ryu and Takayanagi did it for us already. So this second term in this difference is actually this, okay? So we have to replace, so the second term in the difference is what's written over there, but now we have to see what we get when the impurity is there. Okay, so of course you can do complicated and less complicated things, and let me take the simplest possibility of actually including the effect of this impurity. I mean, there are certainly more complicated, more complete ways, but certainly the way which we found covers the important aspects of this. Yeah.
So this is supposed to give you the entropy purely of the impurity, if you subtract those?
Yes.
But entropy is not additive, right?
Okay. What do you mean it's not additive? I mean, maybe let me go on and just show you what I want to do. And then we can discuss this again. I mean, okay, so this definition, which is now in the dark, this is not something I invented. I mean, this is something which people have studied a long time before ADS-CFT. And there's field theory results for that, and this is defined to be the impurity entropy. So, and certainly it's a, okay, so obviously if you add the impurity, you add some extra degrees of freedom. So in that sense, this will be a positive quantity.
You're going to compare this in the CFT also with the same quantity?
With exactly that quantity, yes, exactly.
Sorry, can you clarify what you mean with the back reaction of the ADS2?
Yes, this is exactly what I'm going to write. So this is the next formula. Okay. Sorry, and let me just write the board. I mean, this is what I want to say now. Okay, so as you are asking, so let me tell you how to include the back reaction. Okay. So let's consider a simple model for including the back reaction. And so the idea is, it's the super simplest thing which you can imagine. So let me draw a picture first. Well, before we had let me draw the actual direction in this direction now. So this is our radial coordinate, this is the boundary. Okay, so this is where our spin is. So the simplest possible thing you can do is you just cut your anti-de Sitter space into two halves along this line, and then you glue them together again under the influence of the matter which is localized at this defect. So you should remember what the matter is on this defect. Because I wrote the action this morning, so it's the energy momentum tensor which you get from the action which I wrote this morning. And so there was a gauge field called AAT, and then there was this famous complex scalar which is dual to our condensate. And both of these will enter the energy momentum tensor, and so the energy momentum tensor on this line is then going to tell you how to glue these two halves of the space. Of course, in principle, what you will have to do is to construct a so-called Janus solution for this geometry and so on, so you can do many more complicated things, but let's stick to this very, very simple idea now. Okay, so the idea is cut the BTZ space into two halves. And there's a concept in general relativity which tells you how to glue them together again, and this is the so-called Israel junction conditions. Okay, so what is an Israel junction condition? So it's an equation which involves the extrinsic curvature. So kappa is the extrinsic. Well, okay, so as I said, I cut the space into two halves, and so in principle, each of these halves is going to have some kind of form which we need to determine, and so I can define one extrinsic curvature on this side and another one on that side, but it's sufficient to consider one of them, and then these conditions are going to tell us how to glue these two things together. And depending on what the tension of the matter on this, so I will call this a brane sometimes, but you have to be extremely careful because it's not a brane in the string theory sense. So essentially, depending on what the matter on these lines does, the space is going to become bigger or smaller, which also means that our geodesics will be either longer or shorter, but this is what we want because we want to change the entanglement entropy. Okay, so this is the extrinsic curvature. And then we have the induced metric on, okay, so this we will call x minus of t, and this is x plus of t, of z, of course. What am I talking about? X plus of z. Okay, so these are the two directions. And then here we have the scalar associated with this extrinsic curvature. This is the induced metric on x plus. So, I mean, let's write this equation for the right-hand side of this, but equivalently, we can also do it on the left-hand side. It's totally symmetric. And then, so the point is that this will be given by the energy momentum tensor of the matter. So there's 8 pi g Newton times the energy momentum tensor. So this is the energy momentum tensor for the matter on the brain. So let me call this brain in quotation marks. I just mean these surfaces which delimit the two halves. Okay, so essentially that equation is going to tell us how we have to glue the two halves together again. And so essentially it will tell us, because we do everything symmetrically on the two sides, it will just tell us how to identify these two curves, which then, of course, changes the entire space. Okay, so in principle now you have to work out what this energy momentum tensor is for the scalar and the gauge field, which we know from the last 3 lectures that I have given to you. And rather than solving all the equations, let me discuss what exactly happens. Because it's essentially the tension which is provided by this matter, which will tell us how the geometry looks like. So let me wipe the board and then draw some more pictures. So essentially, if the tension of the matter is positive, the space becomes bigger, and if it's negative, it becomes smaller. Okay, so what's going to happen is that, so depending on the tension, so which I call lambda on the brain, the original space becomes bigger or smaller. Well, okay. I mean, the space is infinite anyway, but if you consider a region around this defect, then this applies. Okay, so if we have a positive tension, then what happens, I hope you see parts of this figure up there. So what happens is that, okay, so if I consider the left-hand side of this picture and the right-hand side, then, okay, so if I cut the space in half at 0 tension, then I just get a vertical line here. But what happens if this Israeli reduction condition is going to tell me that if I take the tension to be larger than 0, then actually I get a space which is bigger, and this limit, so this is the space, and here on the other side it will be like this. Okay, so this means now I glue these two halves together according to this Israeli junction condition, and then the entire space will be bigger as before, because these wedges are added to what I had previously, okay? Conversely, if lambda is less than 0, so you have a negative tension, it's the other way around and your space becomes smaller. So then if on the left-hand side you will cut like this, and on the right-hand side you cut like that. So now if you glue the two halves together, this will be smaller than what you had before, when the tension was 0. So now, in our case, when we put this matter, the tension will always be positive, so the space becomes bigger than what we had before, but that you expect, because if we add the impurity to our space, then we obviously add some degrees of freedom, which means that this geodesic has to be longer than what it was before. And that's exactly what's happening is when you have this positive tension.
Sorry.
Yeah?
The energy momentum tensor
Yeah.
that you have there is the energy momentum tensor you extract from the gravitational theory
Yes.
in 2 dimensions, just
Yes.
the usual definition.
Yes, taking the action which I wrote this morning, and then you vary with respect to the metric and the usual thing.
The second thing, when you say that the space gets bigger or smaller,
Yeah.
it's some non-extensive sense. So, I mean, the geodesic becomes slightly longer or shorter when they cross this junction. It's not like you take out, if I take a piece
Yeah.
that crosses this division,
Yeah.
and call it L, it doesn't become smaller by something that's proportional to L, but something.
Let me show you what okay.
Because I don't understand very well this.
Well, because I haven't finished what I was going to say. Let me wait for 2 minutes. We will come. I mean, I'm about to explain all this. I hope. Okay, so what we did is, we take our action which we wrote this morning, we calculate this energy momentum tensor on the ADS2 first, and then we plug it into this equation, and then we solve this equation numerically. We have to solve this numerically, and then we get a result which I'm now going to draw on the blackboard. Okay, so this negative tension case was just for illustrative purposes, but since it doesn't happen, I'm going to wipe this out. Okay, so now, if in the case of constant tension, these lines are actually straight lines, okay? However, in our case, the tension will depend on the radial coordinate because the matter fields depend on this radial coordinate. So the tension is going to change. So this is the UV, and then we go all the way to the horizon, which is the IR. And along this flow, this line is actually going to bend. So let me just draw this right-hand side, okay, for the theory which I've been discussing the last 2 days. So we solve the Israel conditions numerically. We find the following. So this is the boundary, and this is the horizon. And we take our radial coordinate to go in this direction. So now what happens? Under the influence of this Israel junction conditions, this cut, it starts off with a particular slope here. Now I'm totally exaggerating, but just so you see the effect. So it starts out like this, but then it turns around and it becomes steeper. Okay? So this is the UV, and this is the IR. Now, what you can do, you can fit a linear line according to this constant tension picture, and you can also fit a line here. And then, so if you draw your entangling region and draw a geodesic, then say your geodesic starts here, you see that in that case, it's much longer than in this case, okay? And so this extra piece will contribute to the entanglement entropy. Okay, so essentially I can summarize by saying the larger the condensate, so the condensate becomes larger the more you flow to the IR. And the larger the condensate, the shorter the geodesic and the smaller the entanglement entropy. On the other hand, so we can also say the lower the temperature, the smaller the space. Okay, so small in the sense I'm saying here, okay, of course each of these halves is infinite, but if you draw kind of a volume around this area and consider this box, then certainly you can say that these curves become longer and shorter in a well-defined sense. Okay, so you can say the following things. The lower the temperature, the smaller the space. Okay, let me put this into quotation marks, but you see what I mean. And then you can also say the larger the condensate, the shorter the geodesic. And that's relevant for entanglement entropy. And this means the smaller the entanglement entropy. All right. So now for the field theory side, let me just quote a result of some famous quantum field theorists. So there's quite a lot of people who have worked on this in quantum field theory, and they were precisely calculating this difference, which is called the impurity entropy of some length L. And as I said, this is the entanglement entropy with the impurity minus the entanglement entropy without the impurity. So this is a definition from quantum field theory. And okay, so let me just, so the paper I got this from, but there's other people who have worked on this, CERN, Cheng, Laflorency, and Affleck. And they got this in 2007. And let me, okay, so I need to write the board and let me write this. So Alex, when did I actually start? How long should I? 20? I hope I have 25. But okay. Okay, so now let me write down the field theory result and then tell you that we get exactly from this picture I'm showing to you, we get exactly the same, at least in some limit, and of course in the large n limit. Okay, so these people got the following result for this definition which I wrote for you. And so they get pi, and then there's a length scale called the Kondo correlation length. T is the temperature divided by 6. And then there's a quotient hyperbolic of 2 pi LT. So L is the length of the entangling region, and so this psi k is the so-called Kondo correlation length. And this is a quantity which tells you about the size of this Kondo cloud, so this cloud of electrons around this impurity, but this is very hard to calculate or to measure in condensed matter physics. Okay, and now the message is that we can reproduce this result using this analysis which I was pointing out. So in the gravity approach, and so we have to do the following. Okay, I hope you can't really see this picture. No. Okay, let me draw it again. So here's the boundary. Here's the horizon. And so this, if we were to cut the space without any tension, then it would just be a straight line. Now, so then we can have an entangling region. Say this time we take length 2L to make it symmetric, so then this would be L here and L there. So in the turtle is 2L. Okay, and then now the thing is that, okay, let me just draw the right-hand side, so just keep this left-hand side in your mind. So now we added this brane which curves like this, and here I draw this, this kind of dotted line which was a linear approximation to the slope of this boundary at this point. So let me draw this sine dotted line now in this graph. And so what actually happens, then it will look essentially something like this. Okay, so remember what we are calculating. We are calculating the difference of the entanglement entropy with the impurity minus the one without any impurity. And the with the impurity, we now take an approximation to what happens in the IR. So the result of this difference will be positive because we add more when we add the impurity. However, it will be less than what you have in the UV. Okay? So because we have to see the screening effect. In the UV, this line would be something like this, say. Okay? And the geodesic would be even longer. And then we get the entire Q boxes in our Young tableau which contribute as degrees of freedom to the entanglement entropy. But in the IR, remember that this got reduced. And so this is now indicated by this space being smaller. And okay, so this was supposed to be a straight line. I hope you believe me, this is a straight line. So then essentially I can call this distance d, the distance between here and there. And then this is a straight line, then by some elementary geometry, this would also be d here. So as a very crude approximation, the effect of adding this brane is to enhance my entangling region by a distance d. Instead of L, I add some d to it. So what we have to calculate, so to get the impurity entropy, is the entanglement entropy for a BTZ black hole for an entangling region which is L plus D minus the entangling region with a BTZ black hole where there's no additional brane, so this is the original. Okay? And now what I'm going to do, I take this result of Ryo and Takayanagi, which coincides with the Cardi-Calabrese result here. Here I write the same here, and then now, except that I change the argument, I make this entangling region bigger. Okay? And then you can actually see, so, and we have to do some approximations to make, so essentially, there's a linear approximation which means that there's some limits which we have to take. So L times T has to be very big, whereas D times T has to be very small to make this work. And then, of course, we are in the large N limit as always. And so then, in this limit, our approximation actually works. And okay, maybe I should write down what I'm doing. So the lengthening of geodesic modeled by enhancing the entangling region from L to L plus D. So now if I'm in this limit where L is very big and D is very small in these units, then essentially I get that the impurity entropy, according to this definition, will be D times the derivative, so this is the linear order term, the black hole, the BTZ entropy of this entangling region L. And if you recall the result of Rio and Takanagi, so they have found that this BTZ entropy, so I wrote this earlier, so just to recapitulate, was this. There's a sine hyperbolic of 2 pi LT. So now I'm going to take a derivative of this expression, and so if you do that, then you get a cotangent hyperbolic. And so our result will be 2 pi dt over 3 cotangent hyperbolic 2 pi LT. So now where's the result I want to compare to? There. Okay. So isn't this amazing? This is the same as this, except here we have psi k and there we have this d. Okay. So our d is a geometric quantity which we get from this geometric construction. And here previously I told you this psi k is the so-called Kondo correlation length, which is a length scale which tells you how big this Kondo cloud is, which screens your impurity. So what we have to do, if we identify, so there are some factors of 2 and probably no pi. Okay, let me not worry about these factors. Just say if we say psi k is proportional to d, then the results coincide. So I think this is a super nice result. Okay, so this is the length scale which you have in the field theory. And now we have given a geometric quantity which kind of plays the role of this psi k, which in any case is a very hard to understand or calculate concept in condensed matter physics. And so now we can realize this by this geometric quantity. And I think this is a super nice result. Okay, so
aren't these calculable in terms of the parameters that you already have in the theory? I mean, are these free parameters that you are free? I mean, you can see d on one side and psi k on the other side.
Very good question. So you say now, let me just think. The thing is that this line we can get only numerically. So this means I can calculate this d only numerically for this model, which I have been discussing beforehand.
Yeah.
But of course, well, I can give you a numerical value for this d in our model.
Okay,
and this psi k, I think in condensed matter physics, this is extremely hard to calculate. I didn't find any calculation of this quantity. I mean, there's many studies. I mean, this is one of these unsolved issues about the Kondo model that, I mean, people obviously try to identify this quantity with something. Also, in using quantum quantists, they want to see how the Kondo cloud forms and so on. But I don't think there's a universal accepted result for this psi k inside condensed matter physics. It's one of the
even the conformal field theory methods don't give any definite answer.
I don't think so, because Affleck leaves this as a parameter in his calculation, so then I'm pretty sure it's okay. Good. All right. So in the remaining 10 minutes now, let me move to this Sachdev-Leahy Taif model, which I promised to talk about. And so I hope you have more questions about this, but then let's do it in the discussion session. Okay, so another thing we can do with this model is to calculate two-point functions. And these two-point functions have a very characteristic structure. Okay, so let's go back to the probe limit. So if I mean two-point functions, I really mean retarded and, of course, also advanced Green's functions. So far we can only do the probe limit. And so there are some well-established methods in gauge-gravity duality how to calculate a retarded Green's function. And so now here we had to adapt this to actually apply it to the Kondo model. And so this is extremely recent. So we had 2 papers about this. So it's actually quite involved to do this so-called holographic renormalization which is necessary for calculating these two-point functions in the presence of this defect, and that was the subject essentially of this somewhat technical paper 1612, but there's a shorter one about essentially the physics results, which is this one. So, since I don't have a lot of time, let me just advertise those papers and you can take a look. Okay, so now we adopted the standard methods of gauge-gravity duality for calculating two-point functions and applied them to our Kondo model. And then, so essentially what we find is that the two-point functions so an example for a two-point function is precisely again involving this operator O, which we were discussing all along. So this is exactly for this two-point function, and from this you can calculate the so-called spectral function, which is defined as minus twice the, so if this gives you the Green's function, then the spectral function will be minus twice the imaginary part of the retarded Green's function, which you get from this correlator. So we can calculate essentially for the 0 plus 1 dimensional object, so it only depends on the frequency. If we Fourier transform, we can calculate this down. And so the two-point functions, they exhibit a so-called Fano resonance. So Fano was an Italian physicist, and he wrote this already in 1961, and this is something which occurs, so I think his name was Ugo Fano. And so this is something which occurs, for instance, in quantum dots, and this is so what you have for this quantum dot, so here you have your lead, so where your electrons can go through, and then there's a quantum dot here. Okay, and this has a discrete set of states, and and whereas here there's a continuum of states. So the electrons can either zoom through or they can interact with this discrete set of states. And if you have this discrete set of states interacting with a continuous set of states, then what happens, you get an asymmetric spectral function. And let me just write this, this form of this Fano spectral function, and you can actually show it's a sum of a symmetric and an antisymmetric part with some parameters. So omega naught is going to be the maximum of this function. And this Q here, this is the so-called asymmetry parameter. And then there's the width of this resonance. And okay, so in the denominator we have omega minus omega naught squared plus gamma over 2 squared. And so gamma is the width, omega is the maximum, and Q is this asymmetry parameter. Okay, so when we calculate our spectral functions, we actually see that they have this asymmetry. And I could now have a whole entire discussion of what happens when you go through the phase transition, what happens in the normal phase and in the screen phase. And since I'm running out of time, let me refer you to these papers. And very briefly at the end, mention very quickly a connection to the so-called Zatchev-Kitaev model. So this has received a huge amount of interest in the last year or so for a number of reasons. It has a lot of interesting features, and I can't do justice to this model now in 5 minutes, but let me essentially say that this is a 0+1 dimensional model with a finite thermal entropy at 0 temperature. So, and actually, this model is also obtained using our famous Abrikosov pseudo-fermions. So, how this model? So, Zatchev and Yi obtained this model essentially in 1993, and Kitaev proposed a simplification in relation to ADS-CFT in 2015, which started this new interest in this model. So what you start from is a spin model in a lattice in I think in arbitrary dimensions if you want, but then there's some averaging taking place. So this is your spin model. And now we are going, so these are some Gaussian random couplings which you can average over, and these S's we now rewrite using our Abrikosov fermions. Okay, I will finish in 3 minutes. So the key point is that this model will also have a spectral asymmetry, and which in that case you can relate to this this finite thermal entropy at 0 temperature. So first of all, this model can be reduced to a model in 0+1 dimensions. So we start from the spin Hamiltonian and then use the Abrikosov fermions as before. And so if you remember from yesterday, what we did, we wrote this as in this form. And this you can also do here. And then you take the large n limit, which here, of course, is a vector limit first again, and then average over these random couplings. And once you do that, you get a mean field theory where you have the same theory at every lattice site. So it suffices to look at a single one. So then, this gives a mean field theory which is the same at every lattice site, which means that the model becomes a plus one dimensional model. So just time evolves. And so let me write the Hamiltonian, which is this famous such FD Kitaev. So we have 2n to the 3/2. And then now there's a sum over alpha, beta, gamma, and delta, which go from 1 to capital N, so which is our large N. And then there's these Gaussian random couplings. So now there's 2 indices for every site because we have these 4 fermions. And as expected, there's now a 4 fermion interaction with these Abrikosa fermions. And there's again, we have to impose this extra condition, so there's a chemical potential for the charge density of the Abrikosa fermions. Okay, so this is this model. And then, as I said, the expectation value of these couplings, when you average over this random disorder, is 0. And the mean, there's a mean squared, so this is called J squared then. Okay, so I'm absolutely out of time, but what I want to say is that here you also get a spectral, so this model has a spectral asymmetry. And this asymmetry, very simple, which is the same, which coincides with the one of ADS2 Reisner-Nordström charged black hole at 0 temperature. So Reisner-Nordström black holes also have a finite entropy at 0 temperature. And now, so what Sachev did was to calculate the spectral function both in this model and both in this ADS2 Reisner-Nordström, and he finds the same structure. And so I hope the chairman lets me use another minute to just write the final result, which is, okay, let me run off. So the spectral asymmetry takes the following form. So here he writes it in a slightly different way than this Fano resonance, but this is related. So he looks at the advance and the retarded Green's function, and then shows that this is some even function of some omega minus omega s. So, and this omega S defines the spectral asymmetry. So this is the asymmetry. And then such shift shows that this omega S is given by some Q tilde. So this is the U1 charge of your model, or similarly, so this is the spurious U1 which we got from these Abrikosa Fermions, again, which you can then identify with the U1 of your Reisner-Nordström black hole, and then there's T, H bar, and then there's the variation of, so this is the thermal entropy at 0 temperature. And so then this U vary with respect to some curly Q, and this curly Q is the charge density associated with this. Okay. And the thing is that this result you can obtain both in this model, which is written over there, and for this ADS2 Reisner-Nordström black hole, and it has exactly the same structure, which then also relates to the spectral function. So the main message is that there's a lot of things to do. So there's a lot of interesting structure in all these spectral functions in the 0+1 dimensional models. So I showed you the one for the Kondo very briefly, but these fall in the same class. So this model is also the SYK model. It also has interesting quantum chaotic behavior, for instance. And so this is, I don't think there's a well-established gravity dual of this model yet. So where you really have a field operator map and so on. So this would be super interesting to develop a new example for the ADS-CFT correspondence here. Okay, so this brings me at the end of my 4 lectures, and I hope I gave you some overview over these interesting aspects of quantum impurities in the context of ADS-CFT. And there's clearly a huge amount of things to do. And if I was very quick now at the end, please use the discussion session to ask me more questions. Thank you very much.